So, the subject that I've probably tutored the most over the last couple years is Cal 1, and something that I noticed was a surprising amount of students come into Cal 1 without having a firm grasp on the unit circle, sine, and cosine, and this got me thinking, why would this be? What is it that's so tricky about the unit circle for people who are learning it for the first time? Now, I'm sure there's a lot of answers to this question, but something I came up with was I realized we have a lot of things that sine and cosine represent. Sometimes they represent these waving graphs going up and down, and other times it seems like they represent the coordinates of an arrow that moves about some circle. And didn't this whole thing start with triangles, where we were looking at three sides, the opposite, adjacent, and hypotenuse, and sine and cosine represented the ratios between those? Is that still related to the sine and cosine whose graphs oscillate up and down? And on top of this, just to make matters worse, we're no longer using degrees. Why did we switch from degrees to radians in the first place? So my goal is to answer all of these questions in a 3-part series I'm calling Understanding the Unit Circle, and I think a good place to start is on understanding radians. To begin, let's put ourselves in the shoes of an ancient mathematician who's been tasked with coming up with a way of measuring rotation around a circle. Probably one of the first ways we'd think to do this is by splitting up the circle into equal pi slices. We could then call this first angle 1 degree, this second angle 2 degrees, this third angle 3 degrees, and so on. But there's a problem here. What if somebody asks you to divide this into thirds? Well, okay, we'll just add in these slices, and now we'll call this 1 degree, this 2 degrees, this 3 degrees, and so on. But what if somebody now tells you they want to be able to divide that first quadrant in half evenly? Well, you'll have to introduce this line, which means to keep everything consistent, you'll have to introduce all these other lines. And at this point, maybe we feel a little silly for thinking the solution was in dividing our circle into even pi slices. And how will we know when to stop? Couldn't we just keep dividing it more and more, and wherever we decide to stop is totally arbitrary? So at this point, we might be thinking we want to find a way of measuring angles around a circle that doesn't involve us arbitrarily picking a number of slices. But if we don't pick a number of slices, how do we do it? After thinking a while, we might come up with the idea of labeling angles by the distance you have to travel around the circle to create that angle. But we don't have inches or feet in this diagram, so what are we going to use to measure our distance traveled around the circle? So first, let's create some axes so that we can actually give some numbers to things, and we'll make this circle here have a radius of 1. Let's pluck out that radius, and notice that this is a line that we know has a length of 1. We can now imagine taking this line and flattening it over the outside of the circle, and creating an angle out of wherever this line gets us to. Since we used 1 radius length to get this angle, we might find a fitting name for this angle 1 radian. We can now create a second radius length and imagine lining it up with the previous one that we laid down. This angle would then be called 2 radians, since we used 2 radiuses to get us here. We can create a third radius and lay it down again, and notice that this is so close to getting us halfway around the circle. 3 radians gets us almost 180 degrees. And at this point, we're really curious what that remaining length is we'd have to travel to get halfway around the circle. We could take that length out and measure it, and what you'd find is that it's approximately 0.14159. And at this point, you're probably a little suspicious of what's going on here. I mean, we're dealing with circles, you see a 3, and you see a 0.14 on the screen. The first thing we're thinking is pi. And sure enough, we can add this length on to what we already have to get 3.14 radians around the circle, or just pi. And I think it's a good idea to very quickly just stop and reflect on why we're saying this is pi radians. It means it took us pi radius lengths to get halfway around the circle, and in that sense we can say pi radians is equivalent to 180 degrees. We're now going to take this one piece of information and use it to construct all the other degrees around the circle. We can first say that half of the way to pi is just 1/2 of pi, or pi over 2 radians, and 1/4 of the way to pi is just 1/4 of pi, or pi over 4 radians. Furthermore, we can move over here to 3/4 of the way to pi and call that 3 pi over 4 radians. And notice that we could call pi radians 4 over 4 pi radians, which means adding one more fourth of pi to that will get us 5 over 4 pi radians. Adding another fourth to that will get us 6 over 4 pi radians, which we can simplify to 3 over 2. Adding another fourth to that will get us 7 over 4 pi radians, which we can't simplify. And once we're all the way back around, we're at 8 over 4 pi radians, or just 2 pi radians. And notice that 2 pi radians is at the same position as 0 radians. Also, before I move on, I should note that each of these angles is exactly what they look like they would be in degrees. Pi over 4 is 45 degrees, pi over 2 is 90 degrees, and so on. So if you can imagine where the radians are in your head, you can convert to degrees without even doing a calculation. Now, we split the top half of our circle into 4 equal pieces, but what if we had chosen some other number of pieces? So let's take this top half of our arc and divide it into 3 equal pieces, all of the same length. Because we know each piece has the same length and there's 3 of them, we know that this first angle theta must be 1/3 of the way to pi, or pi over 3 radians. Similarly, this second angle must be 2 over 3 pi, or 2 pi over 3 radians, and this last angle we know is 3 over 3 pi radians, which means that moving one more third gets us to 4 over 3 pi radians. Moving another third past that gets us to 5 pi over 3 radians, and moving this final third gets us to 6 pi over 3 radians, which simplifies down to 2 pi radians. Again, each of these angles is exactly what it looks like it would be in degrees. Pi over 3 looks like it's at about 60 degrees, and it's at exactly 60 degrees. And similarly, 2 pi over 3 is just 2 of those 60 degrees, so it's 120 degrees, and adding another 60 gets us to 180, or pi radians. So we could technically take the top half of this circle and divide it into as many pieces as we want to create whatever angles we want. But the last one I'm going to cover, and the last one you'll probably need to know for any classes you're going to take, is dividing it into 6 equal pieces. When we do this, that first angle theta gets us 1/6 of the way around to pi, or just pi over 6. The next angle will be 2/6 pi radians, which we know is just pi over 3 radians. And then the next angle will be 3 pi over 6 radians, which we know is just pi over 2. Doing this game again, we'll get 4 pi over 6 radians, or 2 over 3 pi radians for the next angle. We'll get 5 pi over 6 radians for the one after that. And for this one, we'll again get 6 over 6 pi radians, or just pi radians. Adding one more sixth onto that gives us 7 over 6 pi radians. Adding another sixth onto that gives us 8 over 6 pi radians, which is the familiar 4 over 3. Adding another sixth gets us 9/6 pi radians, or 3/2. Adding another sixth onto that gives us 10 pi over 6 radians, or just 5 over 3 pi radians. Moving to this next angle gives us 11 pi over 6 radians. And finally, moving this last little bit gives us 12 pi over 6 radians, or just 2 pi radians. Again, we can find the degrees of each of these angles just by looking at them and guessing what they look like they should be in degrees. For instance, pi over 6 is 30 degrees, pi over 3 is 60 degrees, pi over 2 is 90, and so on. And this only works because we picked really easy to guess angles. If we had picked something like dividing the top half into 5 pieces, this would be a little trickier. And you'd probably want to use the formula, which is 180 divided by however many pie slices you made in that first top half of your circle. So for instance, when we divide it into 6 even pieces, we'd say 180 divided by 6, which gives us 30 degrees, which is exactly what pi over 6 is. Now, radians don't really come naturally to anybody at first, and I don't want to act like they do. So please go back and watch the last couple minutes of this video until you feel really comfortable about how we label radians and what it means for a certain radian to be in a certain position. But before the video ends, I want to talk briefly about some of the applications of radians and why they're preferable in most cases to degrees. For instance, take a look at this yellow arc we have. If we were measuring theta in degrees, this would be the formula for the length of that yellow line. But now that we are measuring theta in radians, the formula is very simple, just theta times r. Similarly, if we're looking at the area of this pie slice, often called a sector, in degrees the formula is this mess. But in radians, the formula is as simple as 1/2 theta r squared. I'm going to take the applications one step further, so for those of you that aren't interested, feel no pressure to watch this part of the video. But for those of you who are, in physics we often want to describe the motion of a rotating object. And in radians, we know that the arc length of some part of this circle is r theta. Applying a little bit of calculus, we can say the velocity is dl dt, or just r d theta dt. And in physics, we often call that omega, the angular frequency. And keep in mind that these formulas are pivotal in physics, and if we weren't in radians, they would be really ugly. So hopefully this video makes you feel a little more confident about radians. In the next video, I'm going to get into sine and cosine, where they come from, and how we find the values of sine and cosine at different angles.